Hello friends. Today, we are going to learn about pressure vessels, which are used in various industries. Here we will learn about their types, material of construction, maintenance procedure, and usage in different sectors. For starters, a pressure vessel is a closed container designed to hold gases or liquids at a pressure significantly different from ambient pressure, commonly used in the petrochemical sector for storage, processing, and transport of fluids. Let us know about the types of pressure vessels being used in the petrochemical sector. Storage vessels. They are used to store raw materials, intermediates, or finished products in liquid or gas form in a controlled environment. Boilers. They convert water into steam for process heating, power generation, and other process requirements within the industrial plant. Heat exchangers. They transfer or exchange heat between fluids, essentially for process control and energy efficiency purposes. Distillation columns. They separate fluid mixtures based on their volatility differences and provide different products as per their boiling points. Reactors or process vessels. They are used where chemical reactions or processes like mixing, separation, or agitation occur under controlled pressure and temperature ranges. Decanters and mixers. They facilitate the separation or homogenization of fluid mixtures under pressure. The most common types of pressure vessels are cylindrical, horizontal or vertical, and spherical vessels. In their construction, they have different types of heads that are selected as per the process requirements. The types are: hemispherical head. Hemispherical heads are preferred for pressure vessels that require maximum strength and reliability under high internal pressures. Their unique geometry distributes stress uniformly, allowing for thinner walls and higher pressure ratings compared to other head types, though at the expense of increased material usage and vessel height. Ellipsoidal head. Ellipsoidal heads are a versatile and efficient choice for pressure vessels, offering a good compromise between strength, material efficiency, and manufacturability. Their ability to distribute stress evenly makes them reliable for medium pressure applications, and their moderate depth allows for more compact vessel designs compared to hemispherical heads. Torispherical head. Torispherical heads are a cost-effective and practical solution for pressure vessels operating at low to moderate pressures. Their design, featuring a dished crown and a toroidal knuckle, balances strength, manufacturability, and material efficiency well. They are especially valued in industries that require adaptable, durable, and economical vessel heads for various process conditions. Conical head. Conical heads are specialized pressure vessel ends that provide a tapered, cone-shaped surface. They are ideal for applications requiring efficient material discharge or transitioning between sections of different diameters. While not as strong as hemispherical or ellipsoidal heads, conical heads offer unique advantages in process design, especially where flow direction and collection are important. These vessels are critical for safe, efficient petrochemical operations, each type tailored to its specific process or storage need. Different materials of construction significantly affect the performance of pressure vessels in several ways. The material of construction selection criteria for the vessels is based on the following factors. Strength and durability. Materials like carbon steel offer high strength and cost-effectiveness, making them suitable for high-pressure applications, while alloys can provide even greater strength and allow for thinner, lighter vessels. Corrosion resistance. Stainless steel and certain alloys, for example, nickel and titanium, provide excellent resistance to corrosion, which is critical when handling corrosive substances or operating in harsh environments. Temperature resistance. Some materials maintain their strength and integrity at high or low temperatures, which is essential for vessels exposed to extreme process conditions. Fabricability. The ease of manufacturing, welding, and forming varies by material, influencing cost and the complexity of vessel construction. Weight. Materials like aluminium and composites, for example, fiberglass reinforced plastics, offer a high strength-to-weight ratio, reducing vessel weight, but will have limitations in temperature and pressure resistance. Service life and maintenance. Materials with better corrosion and fatigue resistance generally extend vessel lifespan and reduce maintenance needs. The better the grade of material used for construction, along with non-abusive usage, ensures performance of the equipment will be maintained for longer time, thus reducing maintenance breaks. The most common materials used in the construction of ASME, U-stamped pressure vessels are as follows. Carbon steel, for example, ASTM A516. Widely used for its durability, strength, and cost-effectiveness, especially in moderate temperature and pressure conditions. Stainless steel, for example, 304, 316. Preferred for superior corrosion resistance, making it ideal for vessels handling corrosive fluids or used in hygienic applications. Alloy steels, for example, ASTM A387. Chosen for high-temperature or high-pressure applications due to their excellent heat and pressure resistance. Nickel alloys. Used for their outstanding corrosion and thermal resistance in harsh environments. Aluminium. Selected for its lightweight and good corrosion resistance in very specific applications. Specialty alloys, for example, Hastelloy. Utilized in highly corrosive or demanding chemical environments. Material selection in general depends on the vessel's intended service, operating pressure and temperature range, and the nature of the contents. Here we will be discussing the most common maintenance issues that the industry faces with ASME pressure vessels. Let us know about them. Corrosion. Both internal and external corrosion weaken vessel walls, increasing the risk of rupture and equipment failure. Cracks and fractures. Stress, fatigue, and thermal cycling can cause cracks, especially around welds and joints, thus affecting the sanctity of the process. Weld defects. Poor weld quality or aging welds compromise structural integrity and can lead to leaks or failure of the equipment. Valve, seal, and fitting failures. Leaks or blockages in valves, gaskets, or fittings disrupt pressure control and can cause unsafe conditions. This results in a hazardous condition which may result into serious safety issue. Material degradation. Exposure to extreme temperatures or aggressive chemicals accelerates material fatigue and wall thinning. Wall thinning. Erosion and corrosion can reduce wall thickness below safe limits, threatening vessel integrity. Non-compliance with ASME standards. Failing to adhere to ASME code requirements can result in unsafe operation and legal penalties. Since we have discussed about the maintenance issues previously, now let us see how we resolve them during the shutdown maintenance activity. Pre-inspection planning. Develop a detailed inspection plan based on vessel design, operational history, and risk factors. Lockout/tagout. Isolate the vessel from all energy sources and process lines to ensure safe entry and prevent accidental pressurization. Cooling and depressurization. Allow the vessel to cool or depressurize safely before opening, especially if it operates at extreme temperatures. Internal and external inspection. Conduct thorough visual inspections for corrosion, cracks, deformation, and other defects. Non-destructive testing, NDT. Use methods like ultrasonic, radiographic, magnetic particle, or dye-penetrant testing to detect hidden flaws in the equipment. Thickness measurement. Check the wall thickness to ensure it meets minimum requirements as per the equipment design specifications. Hydrostatic testing. Fill the vessel with water and gradually pressurize to check for leaks and structural integrity. Safety device inspection. Inspect and test all safety valves and relief devices for proper operation. Repairs. Any required repairs must be done by ASME certified professionals. Then it should be verified by inspection and testing as per ASME code. Documentation and certification. Record all findings, actions, and certifications before returning the vessel to service. We should remember that strict adherence to safety protocols, confined space entry procedures, and regulatory standards is essential throughout the maintenance process. The U stamp is for manufacturers certifying that new vessels meet ASME standards. The R stamp is for organizations authorized to repair or alter existing ASME stamped vessels to code. A vessel may have both if it was built new, U stamp, and later repaired or altered, R stamp. Here in the table, the basic differences can be seen. Industries that use pressure vessels include oil and gas, chemical, power generation, pharmaceuticals, and food and beverage. Below is a table summarizing estimated usage percentages across major industries, combining insights from the web search results and general industry knowledge. In case if you need more elaborate information about the maintenance activity, you can check our videos on heat exchanger and fractional distillation column link in the description of this video. Towards the last, we would like to thank you all for taking out your time. We will be back with more industry knowledge in the coming days. Feel free to share your feedback in the comments section below. More insights about the industry can be accessed at our blog mentioned in the description. Have a great day ahead.